This is step paper 3, 2011, question 2. In this question, we're asked to consider the polynomial f of x equals x to the n plus a n minus 1 x to the n minus 1 and so on through until a naught as shown in the first line, where n is greater or equal to 2 and all the a's are members of the integers and a naught is not 0. We're asked to suppose that f of x equals 0 has a rational root p upon q, where p and q are members of the integers and they have no common divisor greater than 1. That is, that they are relatively prime. We're then asked to consider the product q to the n minus 1 times f of p upon q, to find q and to deduce that any rational root of f of x equals 0 must be an integer. Now here in line 1 I am showing the product q to the n minus 1 multiplied by f of p upon q, and in line 2 I have carried out the multiplication. My first term is p to the n upon q, and then I have terms in a, p and q, a n minus 1 times p to the n minus 1, a n minus 2 times p to the n minus 2 times q to the 1 and so on, and all of those that I've underlined in blue are integers. In the third line I give a summary of the same result. The sum under the sigma notation is an integer, and when added to p to the n upon q it equals 0. 0 is an integer. The sum from r equals 1 to n minus 1 under the sigma sign is an integer, and so p to the n upon q must also itself be an integer. And if p to the n upon q is an integer and p and q are relatively prime, then q equals 1. And so that means that any rational root of a f of x equals 0 as shown must itself be an integer. We now have to use this to show that 2 to the power of 1 upon n is not a rational number for all n greater than or equal to 2. And so we consider the polynomial I've underlined in red, x to the n minus 2 equals 0. By the result just obtained, any rational root must be an integer. The possible roots are x equals 2 to the 1 upon n. X is not an integer, that is 2 to the power of 1 upon n is not an integer for n greater than or equal to 2, so there is no rational solution to x to the n minus 2 equals 0 for n greater than or equal to 2. We are now asked to prove that x to the power of 3 minus x plus 1 equals 0 has no rational solutions. By the argument we have developed, any rational solution must be an integer, and integers are either even or odd. So we let p be an integer, and we test to see what an even root would be like by putting 2p in for x. And you will see I've got x cubed minus x plus 1 equals 0, so that 2p all cubed, underlined in red, minus 2p plus 1 equals 0, which leads to the conclusion that 8p cubed equals 2p minus 1, that is, that an even integer can be equal to an odd one, and so we have a contradiction. And so here I am testing for an odd root, and I've put 2p plus 1, which will be an odd integer, in the place of x. So this is like x cubed minus x plus 1 equals 0, and I multiply out I factor that out, multiply out my brackets. That should be squared there. Hold on a minute. Squared. And so if I multiply my brackets out, I eventually arrive at this result here. And then I put it into this form here, 2p plus 1 multiplied by 2 multiplied by 2p squared plus 2p will equal 1 if I add 1 to both sides of the equation. which implies that an even number equals an odd number. This is impossible, and so the equation we have just been given can't have any rational roots, because if it had one, it would be an integer, and we've shown that it can't be even and it can't be odd. In the next part of the question, we are required to prove that x to the n minus 5x plus 7 equals 0 has no rational roots. Once again, by the argument established that any rational root must be an integer, all integers are either even or odd. So we imagine that 2p is an even root, and we put it into the equation. 2p to the n minus 5 times 2p plus 7 equals 0. If we take 7 from both sides and factor out 2 on the left-hand side, we obtain another even-odd contradiction. An even integer can't be the same as an odd one, and so we've shown that this thing does not have an even integral root. We now suppose it to have an odd root, 2p plus 1, and once again I put it in place of the x. So this is like x to the power of n minus 5x plus 7. And so I multiply out my brackets. I have got 2p plus 1 to the n minus 10p minus 5 plus 7, which is 2p plus 1 to the n minus 10p plus 2. That has to equal 0. And so if I do a bit of factorization, I find I've got 2p plus 1 to the n plus 2 lots of 1 minus 5p. If I subtract 2 lots of 1 minus 5p from both sides of the equation, on the left-hand side I have an odd number, on the right-hand side I have 2 lots of 5p minus 1, and I've now produced another odd-even contradiction. I've shown that the equation implies that an odd integer should be equal to an even one, and we have now completed this part of the proof and this question.